Professor Silva Leite from the University of Coimbra, Portugal, and the title of her talk is Generalizing least square problems on Riemannian manifolds. Thank you, Fatima.
Good morning. It's a great pleasure to be here on this special occasion. Well, congratulations, Jair. There are 20 years separating these two pictures. And if you look carefully, they both look very cheerful, happy. So I assume that the path that goes from here to there is quite nice, smooth path, let us say a geodesic. So we have a formula for the geodesic that joins P at time 0 to Q at time 40, time measured in years. And so you can compute the picture at every instant of time if you haven't met Jair before, so you can know how he looked like in between these two pictures. Okay, this is my contribution to your birthday. So what I'm going to do is to somehow show ways to generalize classical least square problems on Euclidean manifolds to any other manifolds. And this fitting, so the problem of fitting curves to given data on a Riemannian manifold. So I will start with some motivation, then revisit the classical least square problems, then talk about generalizing this classical approach. First, to get the Riemannian mean, which is just a particular problem of this fitting curve, in which case the curve generalizes to a point, the geodesic fitting problem, and then if we want to do like polynomial fitting problems, we get into trouble because we don't know what a polynomial is on a Riemannian manifold. So for that, I will present a variational approach for polynomial fitting, deriving the Euler-Lagrange equations, going into some limit cases, and using some convincing arguments to convince you that this approach is nice, and then some concluding remarks. Okay, now the problem of fitting a curve to given data on a manifold is an important problem in emerging areas of computer vision. The underlying models for image and video-based applications have a very interesting structure, the structure of a linear subspace, and so they can be described using the unified framework of Grassmann and Stiefel manifolds, and I will give examples with this Grassmann manifold. Now, possible applications, there are many applications, so some possible applications in this computer vision area are motion, action estimation, age estimation, or expression recognition. Okay, the problem of fitting a smooth curve to given data on a manifold at given times involves two goals which are contradictory. The first goal is that you want the curve to fit the data as well as possible, and another goal, which is the curve should be sufficiently regular, and somehow if a curve fits well, it's not smooth, and if it's smooth, doesn't fit well. So you have these contradictory objectives. Okay, in optimization, when you have a problem like that with two contradictory objective functions, there are two possible approaches. One is that you take one of the objective functions as the objective function, and the other you use it as a constraint, or you optimize a weighted sum of the two objective functions. The classical least square setting uses the first approach, where we want a polynomial curve to fit or to best fit some data, and the curve being polynomial is the constraint, and fitting the data is the objective. Okay, so let us revisit the classical least square problem. We are given points in Euclidean space, and these points are time labeled, so you have a sequence of instants of time, I assume here just for simplicity that they are in the 0-1 interval. And we want to find a polynomial curve of a certain degree that minimizes the sum of the square Euclidean distances from the points, given points, to gamma at the specific times. Okay, this problem goes back to 18th century to Gauss. The solution is well known that the solution is unique, and these equations, which are called the normal equations, can be solved explicitly. So the unknowns here are the coefficients of this polynomial curve. And there is a unique solution as long as there is some constraint on the degree of the polynomial and the number of points that are given. Okay, so when we want to generalize this to Riemannian manifolds, well, the natural thing to do is to replace Euclidean distance by geodesic distance. So we will have this objective function, but then the constraint is what is a polynomial curve on a Riemannian manifold. And there has been several attempts to generalize polynomial curves from Euclidean space to Riemannian manifolds. Different methods that work in the Euclidean space and produce exactly the same thing, the same polynomial. If you generalize these different methods on manifolds, usually you get different solutions. And even end you generalize one of these methods to Riemannian manifolds, you end up with very complicated expressions for these polynomials. In some cases, you get just differential equations that these curves have to satisfy, or sometimes you don't get differential equations depending on the method you use, but you get solutions that are defined implicitly and difficult to solve, except for very few trivial examples where, for instance, you are on an abelian manifold where everything commutes. So this is a hard problem. Okay, but for particular cases where we know explicit forms for these curves, then we can use the first approach. And that's the case for if we want to find the Riemannian mean, or if you want to find the fitting geodesic, as long as you know explicit forms for geodesics. Well, going back here, this problem also works if you just want to find a point that minimizes the square distance from the point to the given points pi, in which case all these equations disappear and you get just the first one, which is the center of mass. So finding the center of mass is just one particular problem. Okay, so I will go through these very simple cases where the first approach works. So for things to work well, I'm going to assume that the data, so I want to find the Riemannian mean, okay, the generalized idea of the center of mass. So we have points. Assume that they lie on a geodesically convex subset of the manifold M, and we want to minimize this functional that is just the square of the geodesic distances from the point P to the given points Pi. And we can solve this, and the Riemannian mean P, this point P, must satisfy this equation here. And the geometric interpretation is very nice. So this means that if you join the point P to every given point Pi, and then by a geodesic, and then take the initial velocity, then the sum of all these velocity vectors has to be 0. That's what it is. Okay, now if we move to the geodesic that best fits, then we also add to the points times. So we have now time-labeled points, and this is the objective function again. And we want to find the curve gamma, which is a geodesic. This is my constraint now. So this can be also solved, but, well, if you know explicit forms for geodesic. So I'm going to show this for the Grassmannian or the Grassmann manifold. Okay, the Grassmannian is the manifold consisting of all k-dimensional subspaces of Rn, but they can be, this manifold can also be identified with set of all symmetric projection operators of rank k. And so you can use matrices to describe these operators. So the Grassmannian, for me, is going to be just a set of symmetric matrices which satisfy these conditions. There have to be projections. P squared is equal to P, and the rank of P is K. Okay? So Sn means the symmetric matrices. The tangent space can be computed, and it's the set of all Lie brackets of skew-symmetric matrices and the point P. And I'm taking the Riemannian metric here to be induced by the Euclidean metric in the symmetric matrices. And so you can compute this Riemannian metric, which turns out to be just minus the trace of omega 1 times omega 2, the omegas being skew-symmetric. Well, it's also known that geodesic equation for the Grassmann manifold, so they are curves that satisfy this equation here, and they can be solved explicitly if you are given initial data. So if the curve, the geodesic, starts at P with this velocity, then this is the formula that you saw to calculate the age of the picture of Jair at any time. Okay? So you are now living, or your picture is living on a Grassmann manifold. Well, it turns out that there is a very nice formula for the geodesic that joins 2 points. So if you are given 2 points, P and Q, and then the geodesic, which is always of this form, can be computed. So you can compute the skew-symmetric matrix omega explicitly in terms of the given points P and Q. And so the geodesic distance from P to Q can also be computed easily in terms of the 2 points, P and Q. And so we can go back to this, well, in the case of the Riemannian mean, you just have to replace the formulas we saw before for general manifolds for this particular case. And so the Riemannian mean of a given set of points on the Grassmann must satisfy this equation. So it's an equation that gives P implicitly. Okay. So these I minus 2 pi are orthogonal matrices. P is in the Grassmann, Q is in the Grassmann, or PIs are in the Grassmann, but I minus 2p are orthogonal matrices, and so this log makes sense. It's the principal logarithm of an orthogonal matrix. And for the geodesic fitting problem, situation is similar, but now for the Grassmannian, where we know all these expressions for geodesic distance, we know what the expression for geodesic is, and if you solve this problem, with this optimization problem with this objective function and this constraint, we end up with what we call the generalized normal equations, which are here. And this is a sum of skew-symmetric matrices that has to be 0. They appear here again, pre-multiplied or with this operator acting on them, and this operator appears when you differentiate the exponential mapping. It appears something like that. They don't look very nice. They define this geodesic implicitly, and no idea how to solve this, I have to say. But at least we can give a nice geometric interpretation for the first one, and for the second, we are still working on it. So they both represent geometric means of something. But the last one is not so natural, so I will not mention it at the moment, so we have still some question marks here. But this first equation here just means the following, that this picture represents. So we have P, that's the geodesic, gamma of T. At every Ti, we want, if we have the points, Pi, that we are given. And if we consider the geodesic joining gamma at Ti with Pi and take the initial velocity, and then you parallel transport all these vectors to the tangent plane at P, then the sum of these tangent vectors has to be 0. Okay? So it's like the point P is the mean of points, let us say Pi hat, where Pi hat is like the parallel transport of the points to this, to a neighborhood of the point P. A parallel transport in the sense that you can now consider the geodesic that starts at P with this velocity, and then at the end of, at a certain time, you have the transport of these points Pi that were given. Okay, so the first equation has this very nice interpretation. The second is also a similar thing, but the parallel transport is done along a geodesic that is not clear at all what it is, so we are still working on geometric interpretation. And maybe if we understand well the geometric interpretation of these two equations, we'll be able to come up with maybe some algorithm to find the solution for this fitting problem. Okay. Back to least square problems on Riemannian manifolds, and now since we don't know what polynomials are, degree greater than 1, so besides geodesics, then I'm going to propose another approach in which we are going to optimize a weighted sum of the two objective functions, minimizing the, so fitting and being smooth. Okay, now, how to generalize polynomials of Riemannian manifolds is the first question. And the problem of finding a cubic polynomial goes back to 1989 with the pioneer work of Noakes and some collaborators. They solved the problem of minimizing a functional like that where m was 1. And this capital D dt represents covariant derivative, okay? So if we were in Euclidean space, this would be just usual derivative, but we are in a manifold, Riemannian manifold, so this is the Riemannian metric, and we are here minimizing the integral of the norm of some higher order covariant derivative of the velocity vector field. And then we have some smooth conditions, boundary conditions, and you may also impose some interpolation conditions, in which case instead of polynomials we'll get pieces of polynomials fitting nicely together. You will get splines on manifolds. Okay, now, this initial cubic spline or cubic polynomial problem has been generalized by, in fact, one of my PhD students, former PhD students, for higher order. And the Euler-Lagrange equations look terrible. This is what they are for general M. This M can be 0, in which case, if it's 0, you are just minimizing length. Okay? And these are here just curvature tensors. So you get something that, for the Euclidean case, these terms are all 0, and you get here just the differential equation of a polynomial of a certain degree. But for manifolds, you get all these curvature tensors here, which make these equations very nasty, very highly nonlinear. But a polynomial curve on M has been defined as any solution of these Euler-Lagrange equations. Or, if you want, a polynomial curve, if this is satisfied on every, let us say, every intermediate interval. If you have your whole interval 0, 1 partition into smaller intervals, then you have, this has to be satisfied on every short or intermediate interval. Okay. So again, we have these equations. We don't know how to solve them, but we are going to use this idea that polynomials minimize this functional, and we are going to propose a variational approach to least square problems, in which we do this trade-off between being smooth or fitting and being smooth. And so this is the functional we propose. So we have points, time-labeled points, and we want now to minimize in a space of functions this functional where the square distances are here, and here the functional that gives rise to polynomials in Euclidean space. This lambda is a positive number that we call is a parameter, positive parameter. We call it a smoothing parameter. In a while, it will be clear why we call this a smoothing parameter. Okay, and I'm going to assume that the gamma, that the curve I'm looking for, belongs to the family of CM curves in the whole 0, 1 interval, but smooth C infinity on every subinterval. Okay? Okay, and the solutions have been called smoothing geometric splines. Well, we can work out the Euler-Lagrange equations for this problem, and we end up with this theorem, which says that, well, is a necessary condition for a curve to be a solution of this problem I just formulated. Well, gamma, in fact, is twice as much differentiable as initially required, satisfies this equation, which is the equation for the polynomial splines, okay? And in addition to that, it satisfies a bunch of conditions at the boundaries and at every point Ti. Looks nasty, yeah? So let us go down to earth and see what this means when m is 0. So when m is 0, we are talking about geodesics. We have already seen the geodesic case when we do it directly, generalizing the classical approach. Now I'm going to do it with this variational approach. Okay, so we now have, we want to minimize length, but we also want to minimize the square geodesic distances. Okay, and it turns out that in this case, it's just going back to the previous slide and making m equal to 0. So we get that gamma is a solution for that problem if gamma is indeed just C0, just a curve, and satisfies this equation. And this is the equation for geodesic, but satisfies this equation on every subinterval. So what we get is that gamma is a broken geodesic. Yeah? And in addition, it has these conditions at the boundaries and at the points. And here it's nice to see why we call lambda this smoothing parameter. Because in addition to that, so it's a broken geodesic that has to satisfy some conditions. This first condition, that the derivative at T0 plus is indeed proportional to the velocity of geodesic that joins gamma at T0 to P0. But if we go to the intermediate point Ti, then the condition is that this difference, which is the difference between this final velocity vector and this initial velocity vector, is proportional to the geodesic that joins gamma at Ti to Pi. So it's clear from here that the bigger the lambda is, the smaller this difference is. So you can imagine what happens when lambda tends to infinity. So this discontinuity in derivative goes away, so you get a smoother and smoother curve as lambda goes to infinity. And here we have a similar situation. So lambda is what we call the smoothing parameter, that here is clear what it's doing. Well, it turns out that at what time did we start? Oh, I think I'm too fast. Anyway, I may speak slowly, but anyway, if we go earlier for lunch, that's not a problem. Okay, it turns out that when this smoothing parameter tends to 0, the smoothing geometric spline approaches the interpolating spline that goes through the given points, okay? So that's kind of natural. Lambda goes to 0. Lambda is smoothing parameter. So you lose smoothness, but you get fitting. Perfect fitting, not fitting. Interpolation, yeah, the best fitting that you can have. And when lambda goes to infinity, the smoothing geometric spline approaches, and this is interesting, approaches a smooth curve on the whole interval. And moreover, that curve satisfies this equation, which has a much less degree than the one you saw before. Yeah? Okay. dm. So the covariant derivative of order m of gamma dot is 0 in the whole interval. And we know then when m is 0, this is just the equation of a geodesic. What are these curves? What are the curves that satisfy this equation for m greater than 0? Well, I think Velimir is going to like this because what can we say about these solutions? Because they meet rolling without slip and twist. Yeah? Okay, so I say that gamma, that satisfies that equation, is an unrolled Euclidean polynomial. I have to explain what this is. Assume that our manifold and its affine tangent space at the point P are both embedded in some Euclidean space, and this is always possible. Assume that M rolls over the affine tangent space at a point without slip and without twist, so with this, well, with some holonomic and some non-holonomic constraints. And, well, if M rolls over the affine tangent space along a curve that satisfies this equation, the unrolled curve, the development curve, satisfies this equation here. So it's a polynomial of degree m. And of course, because if m rolls on this affine tangent space, the affine tangent space also rolls on m, and the rolling map is just inverse. So we can say that if you roll the affine tangent space along a polynomial, the curve, the development curve on the manifold M satisfies these equations, so which is very nice because we knew that these equations are not the equations of polynomial curves on a manifold. But somehow here they appear as in this limit process. Yeah? So you have polynomial splines, and with this depend on this lambda parameter, and as lambda goes to infinity, these curves are unrolled Euclidean polynomials. Okay, now some pictures to help understanding what's going on. Still for m equals to 1, so in which case we had a broken geodesic, but as lambda goes to infinity, this broken geodesic is going to become smoother and smoother and smoother, and you end up going to so when m is 0, this equation just gamma dot equal to 0. So it's just a point, yeah? So that's what happens here. So I have the Euclidean here and the spherical here, and this is what happens. For lambda equals to 10 to the minus 3, they really look like this broken geodesic interpolates the data. But if you start increasing lambda, look at what's happening. This broken geodesic shrink somehow and become smoother, and increase lambda again, and in the limit, you will get to the Riemannian mean, or in this case, to the center of mass of the given points. And here on the Riemannian mean. Okay? So that's what happens for m equal to 0. Okay, going back to the Grassmannian. Well, the Grassmannian can also be realized as a homogeneous space. And I'm going to show this just for the cubic situation, in which case we were minimizing the square norm of the covariant acceleration and at the same time the geodesic distance from the points to the, in this case, to the cubic, okay? Okay, so the equation for the cubics is this one here. But it turns out that for homogeneous spaces, this equation reduces to a differential equation on the tangent space at the point P. Well, double brackets also appear frequently in my slides, and he is one again. So you have this differential equation now on the tangent space. V triple dot equals to V bracket V dot. I haven't seen any explicit solutions for these equations, except, well, if you want to solve them, you would have to put some boundary conditions here. And I have not seen any solutions except when the cubics are just reparametrized geodesics, but they may not fit the boundary data. I mean, only for boundary data, which is very specific. And then the smoothing conditions reduce, okay, because now we, on this Grassmann manifold, we can compute easily the velocity vector along geodesic. So you have all these expressions here, these conditions, in terms of the logarithm of these orthogonal matrices that are formed with the points on the Grassmann manifold. But again, we are always getting to a kind, which is for us a dead end, yeah? And so if someone can open some doors and maybe this gets some nice results, but so far we are always trapped into some equations that we cannot solve. Maybe, well, you will have to use some other, well, generalized methods to solve differential equations, but to manifolds, so integration on manifolds. Okay, now, why do I, now it comes to a point where I want to convince you that this approach is the right one. Maybe not, I don't want to say that so strongly, but we are convinced that it's a nice approach because in Euclidean space, it gives us the classical solution. So let us do it when m is Rn. So that's what we are minimizing. Now we have Euclidean distance here. Here we have just usual derivatives instead of covariant derivatives. The necessary conditions now are that the curve must satisfy this linear differential equation and some constraints on the intermediate points and the boundary points. Okay, now, when lambda goes to infinity, as before, the smoothing Euclidean spline approach is the polynomial of degree m that solves the classical least square problem. I'm not going to show you how to get there. Well, we start with a polynomial of degree 2m plus 1. Then you take into consideration that this derivative is just a constant. Then you go to these several conditions, and you end up with a very interesting thing, which is that the constraints you have in fact, well, we have already considered that lambda goes to infinity, and in that situation, this constraint is nothing but the first equation in the normal equations, the classical normal equations, and you will get all the normal equations which are equivalent to these constraints on the derivative at the intermediate points. Okay, just some more illustrations, now not just with the geodesic case, but when m is 2. So when m is 2 and lambda is small, we have this kind of cubic curve that interpolates. And as lambda is going to increase, you will see it becoming smoother and smoother and will converge to a geodesic. That's what happens. And pretty soon, for lambda equal to 10, you already see this straight line. Yeah? So the solution of the classical. And here for m equal to 3, it's a similar situation. In this case, as lambda increases, you are going to converge to a quadratic curve. So that's what we observe. Yeah? Increase m, so it will converge to a cubic polynomial. And that fits the data. Well, should be happy. I'm much quicker than I thought I would be. Conclusion, I got to the conclusions. Well, the problem of fitting a polynomial curve to given time-labeled points on a manifold can be tackled in two ways, as I explained. One is the direct generalization of the classical least square problems. If you know explicit forms for polynomial curves, in general we don't, but even in the cases we know, solutions are defined implicitly and the geometric interpretation still lacks clarity. The other is a variational approach, which is a trade-off of the two objective functions, and you use this if no explicit formulas for polynomial curves are known. In this case, we get highly nonlinear differential equations that lead to complicated problems of numerical integration on manifolds. The good news is that this variational approach applied to Euclidean space arises or gives rise to the solution of the classical least squares problem. And that's it. We can go for lunch. Thank you.
And before lunch, we have time for some questions.